Everyone can see the screen?
Yes, sir.
Okay. Okay, Utkarsh, just let me explain again. This water table, I think many of you have still doubt in this water table. See, this is the diagram you should remember. This diagram you should remember. See, very simple. See, there are two zones. You just demarcate with two zones for water table factors. Okay. So you see, one zone you just take up to this df. That means what I am saying, you just take for one zone up to this. So this is what? This is up to the depth df, and the other zone you take from this base of the footing to the limit of influence. So limit of influence will be up to the depth b. So if you want to find out the water table, see, if the water table, this water table, let's say this is water table, if it is somewhere here, then it is outside the limit of influence. So when it is outside the limit of influence, then what will happen? In that case, your Rw1 will be 0, Rw1 will be equal to 1, Rw2 will be equal to 1. What is the use of the water table correction factor? Water table correction factor actually reducing the bulk unit weight of the soil. So see, in this portion of the soil, let's say in this portion of the soil, if you determine the bulk unit weight of soil, in this portion of the soil, if you determine the bulk unit weight of soil, and if the water table is remaining here, then what value of gamma you will be using for these two? You will be using the value as gamma, right? Now once the water, let's say rain starts, and then water table rises up. So rises up, and it just reaches the limit of influence. So when it just reaches the limit of influence, that means when it is just reaching this point, okay. So at this level, this limit of influence, if you see the water table correction factor, I think we have written somewhere here also water table correction factor, somewhere formula we have written. Yes, this one. Sorry. Let me little bit increase it. See, these two are water table correction factors we have written, right? Control C, I am bringing it down. Okay. So you see, this is the two factors we have written, right? So Rw1 and Rw2. Now you see, when this limit of influence is just reaching this point, that is water table is reaching this limit of influence, at that time what is happening? At that time you see this Rw1 factor, Rw1, this is going to remain 1, because you see this portion of the soil will not be getting impacted anyhow by the water table, because water table is now here. So there is no question of water table being present over here. So this Rw1 factor is not going to be affected anyway. So it is going to be 1. Okay. Now if you consider Rw2 factor, then Rw2 factor also at this point when the water table is lying, that means just at the limit of influence when the water table is lying at this level, okay, at this level when water is lying, at that time also you see the value of Rw2 also will remain 1. You understand why? Because you see, when the water table will reach here, your dw dash, this dw dash value will be how much? This dwd dash is being measured below the base of the footing. Okay. So this dwd dash value, when it is reaching, when the water table is reaching here, this dwd dash value will be equal to b. So when it is equal to b, then it is b by b is equal to 1. So 1 plus 1, 2, 2 into 0.5, that is going to be equal to 1. Is it clear? So your Rw2 value, which will be dependent on the bottom portion of the footing, presence of the water table at the bottom portion of the footing, that will become 1. Now you see water table, let's say, reaches over here at this position. So at this position when it reaches, you still notice the water table is not affecting anyway at this level above the base of the footing, it is not affecting anyway. So when it is not affecting anyway above the base of the footing, then Rw1 factor will always remain 1. Till that point Rw1 factor will remain 1, because water table cannot come up to down, it will be going from down to up, right? When the rain will start, when the water table will rise up. Okay, so when the water table rises up, so rises up means when it is reaching at this level, it hasn't yet reached the base of the footing. So when it hasn't yet reached the base of the footing, till that point your Rw1 will be remaining equal to 1. You need not to bother about Rw1. Now you see, at that time your Rw2 factor will depend on this dw dash value. So dw dash value, so when this water table reaches over here just at the base of the footing, you are getting, when the water table is just reaching at the base of the footing, that means at this level water table is coming, at that time see your dw dash value is becoming equal to 0. So this value is becoming equal to 0, and when this is becoming equal to 0, you see 0 by b is 0, so 0.5 multiplied by 1, Rw2 value will be equal to 0.5, and that is what you should understand. See, when this water table has reached this level, Rw2 equal to 0 means what? Suppose you have a saturated soil, so if you have gamma saturated over here, so you see when the water table has reached over there, then the total portion of the soil is under submerged condition. So when the submerged soil is under the submerged condition, if you remember from the basics, very starting and basics of soil mechanics, you see your submerged unit weight of soil is just half of the bulk unit weight or saturated unit weight of the soil. Okay, and that is what is being considered. Basically, you see, when your gamma sat, suppose your gamma saturated value, if it is 18, then how much will be the value of your gamma submerged? Generally what is being done, 18 minus 10 you do. Okay, actually you should subtract 9.81. So you will see it is almost half. So the submerged unit weight of soil is basically almost half of the saturated unit weight of the soil, and that is what is being considered by this Rw1 factor. Okay, sorry, Rw2 factor. Now you see, when this water table has reached at the base of the footing, then also you notice this df value is going, dw value is going to be equal to df. So you see, if I consider Rw1, then df will be equal to dw. So dw is going to be equal to df. So if you put over here df or d, then df and d is df, then df by df is equal to 1 plus 1 2 into 0.5, that is going to be 1. So that means up to the base of the footing, till the water table reaches the base of the footing, the value of Rw1 will be always 1. There will not be any change in that. Now when the water table further proceeds and reaches over here, at that time your obviously the soil at this portion below the base of the footing will be under submerged condition. Okay, so obviously in that case your Rw2 value will be always remaining 0.5. However, you see this Rw1 factor will also now reduce, because you see this dw will be lesser than this df or d. So this value will be lesser than 1. So 1 plus some value multiplied by 0.5, so it is going to reduce, and that way Rw1 will basically reduce the submerged unit saturated unit weight or bulk unit weight of the soil. Then if you see this water table further increases and it reaches the ground level, so when it reaches the ground level, what will happen? This dw will become equal to 0. So if dW is becoming equal to 0, in that case your Rw1, you see, it will become equal to 0.5. That means, you see, when the water table is reaching the ground level exactly, at that time what is happening? The soil above the base of the footing and the soil below the base of the footing, totally will be total soil will be under the submerged condition. So when it is under submerged condition, so at this point when the water table reaches, at that time only the value of Rw2 will be equal to 0.5 as well as your Rw1 will be equal to 0.5. Is it clear now to everyone? Utkarsh?
Yes, sir. Clear.
Clear? Okay.
Yes,
If you
sir.
if you
Yes.
have any more doubt, you can ask. Okay, because see, you should not have any doubt now about this water table correction. I have tried to explain you step by step, and also the problem I have explained step by step. Okay. So see, unless and until you work out your problem by hand, you will not be able to get exact feeling. Again confusion will come up. Okay. So first solve whatever the problem I have given you in the previous yesterday. I think I have given you one problem in the assignment. You try that first. After that I will give one or two more problem on this with different conditions and all. Okay. So in that case, by that way you will be getting more clear about this concept. Okay. But conceptual understanding you should be having very clear. Okay. And it's very simple. See, it's very simple to understand. Okay. Let's go. Let's now move to next part. So we are discussing about this one, right? We are discussing about IS 6403/1981, right? So have I opened it? No. Where is it? IS 6403. Yes. So is there any doubt about yesterday's IS 6403 understanding? Do you have any question on that? Have you understood these two formula clearly? I have explained yesterday.
No, sir. Again.
You haven't understood. Okay.
No,
Anyone
sir.
else? Anyone has understood it clearly or no? Okay. Let me explain again. No problem. Okay. So see what this standard code is saying. See, it is saying the following formula shall be used for calculating ultimate net bearing capacity in case of strip footing. This is very important. Okay. So what is Terzaghi's formula? Terzaghi's bearing capacity formula is for ultimate bearing capacity and considering the general shear failure, and it is given for what? Strip footing. So if you go to Terzaghi's bearing capacity formula, so Terzaghi's bearing capacity formula is nothing but this one. Yesterday I have explained you. So Terzaghi's bearing capacity formula is QU is equal to, no, sorry, not this. Terzaghi's bearing capacity formula is nothing but this one, CNC plus gamma D NQ plus 0.5 gamma B N gamma. And this formula, if you understand clearly, then you see this is actually Terzaghi's bearing capacity formula, right? And this formula is for what? This formula is for strip footing and for general shear failure, isn't it? So Terzaghi's bearing capacity formula, and it is for general shear failure. Now if if you see Indian Standard Code, what Indian Standard Code is saying? See, Indian Standard Code is saying the formula is given in Indian Standard Code for not ultimate bearing capacity, rather it is given for net ultimate or ultimate net bearing capacity. And you see that from definition what we know, if you go back to the definition of net ultimate bearing capacity, where was it? This one. So net ultimate bearing capacity was what? Net ultimate bearing capacity we have defined as QNU, and QNU is nothing but QU, which is the ultimate bearing capacity, minus gamma into dF. And exactly that, if you do it, then you will get the Indian Standard Code formula. So what is Indian Standard Code saying? Indian Standard Code, if you notice, it is giving you the ultimate net bearing capacity, and ultimate net bearing capacity in Indian Standard Code is defined as QD. Okay, so instead we are defining it QNU. So if I write it here QD also as per Indian Standard Code, so you see QD if I write, so what is going to be QD? You tell me, you will be able to only tell me. So what will be QD? What is QD? QD is net ultimate bearing capacity. So what can I write for QD? Tell me anyone.
Q minus surcharge load.
QU minus, bolo?
Gamma D.
Surcharge load.
Yes, QU minus surcharge. Absolutely correct. So QU minus, I am writing gamma into D. That's what you will be writing. So what is the value of QU? The value of QU, you see this one. The value of QU, if you replace from Terzaghi's bearing capacity, which is given for strip footing and general shear failure, this value just I am replacing this QU, you see. So this will become this CNC gamma D NQ plus 0.5 gamma B N gamma minus gamma D. Okay. Now if you simplify this equation, so what will become? What it will become? You see, just you take the common term, just you take gamma D as common. This is having gamma D and this is also having gamma D. So if you take gamma D common, then what will it will become? Gamma D common means NQ, and from this if I take gamma D common, that means this will become minus 1. Is it now clear? So the formula will change to this.
Yes, sir.
So you see CNC gamma D NQ minus 1 plus 0.5 gamma B N gamma. And what is this? What is this? This Terzaghi's bearing capacity formula. This is strip footing, general shear failure, and this has given ultimate bearing capacity, right? This has given ultimate bearing capacity. Now what we have achieved here? So this one, you see, this is actually, you notice, this is actually Terzaghi's bearing capacity formula only. This is actually Terzaghi's bearing capacity formula only. What we have done, instead of ultimate bearing capacity, we are writing it in the form of net ultimate bearing capacity. And from this net ultimate bearing capacity, if you are simplifying, we are getting this formula. And that's why the formula, whatever is given in Indian Standard Code, it is written, if you notice, it is given for strip footing, it is given for general shear failure, and the formula gives net ultimate bearing capacity. And the formula will take in this form. CNC gamma D into NQ minus 1 plus 0.5 gamma B N gamma. And that's what you see, that's what is being written here also. See, this is what is written. So if you see this formula, this is exactly the same, right? If you bring it over here, then you see this and these are same or not? Tell me. QD equal to CNC plus Q. What is Q? Q is nothing but gamma into D. NQ minus 1 plus 0.5, that means here it is written half. Here gamma is written first, here B is written first. So B gamma N gamma, that's what it has written. and we have written gamma d n gamma. So is it clear now? Is it clear now?
Yes, sir.
So we have understood this. So this formula is for Terzaghi's, this formula is as per, this is given as per IS 6403, right? And this is for what GSF, general shear failure, and this is for strip footing. This is for strip footing, and this gives actually the net ultimate BC, bearing capacity. Okay, now you see, if I want to have this formula applicable for local shear failure, then what I'll have to do? If I want to apply this formula for local shear failure, then what actually Terzaghi has said? So Terzaghi has said, if you remember, Terzaghi has said that if you want to change the general shear failure formula to local shear failure formula, what you will have to do? You will have to change the shear strength parameters, right? So what are the shear strength parameters of soil? So shear strength shear strength parameters of soil. What are the two shear strength parameters of soil? Tell me.
Sir, cohesion or internal angle of friction.
Yes. So basically the two factors are these, right? C and phi, right? C and phi, correct? So let us come down. So shear strength parameters are these two, C and phi. Let us remove these terms. So basically C and phi, these two are the factors, isn't it? Shear strength parameters. So what Terzaghi has said, so if you want to make this formula, this QD formula applicable for local shear failure, so if you want to apply this formula for, let's say, local shear failure, then what you will have to do? You will have to change this formula. So local shear failure, if you want to calculate, then for local shear failure, what Terzaghi has said? Terzaghi has said you change this C and phi to its mobilized value, right? And what is mobilized value? Mobilized value means because of the local shear failure of the soil will not obtain its full capacity of shearing strength. That is what is mobilization. Okay, so fully mobilized soil will not be fully mobilized in that case. If the soil is fully mobilized, then it will be having its full strength, that is full C and full phi. So if you consider the mobilized shear strength, so that means if instead of C, if you consider it as, so C, let us write it in caps, then it will be better. So if I write it C, then mobilized C, that is Cm, and as per Terzaghi only, what Terzaghi has defined? For Terzaghi, for local shear failure, Terzaghi has defined mobilized shear strength of mobilized cohesion is nothing but 2/3 of C, and 2/3 of C means, you see, it is nothing but 0.666, so 0.67 C, nothing else. Okay, so if I want to change this formula for the local shear failure, then what I'll have to do? I'll have to change this value of C to 2/3 C. That is the first thing I'll have to do. And second thing, if you remember what we have discussed, if I want to have this mobilized angle of friction, then if I want to have this mobilized angle of friction, I cannot write this one. I cannot write phi m is equal to, 2/3 of phi. I cannot write this. Just like cohesion, I cannot write this, it is not correct, it is not correct. So what Terzaghi has defined, so to get the mobilized angle of internal friction, what you will have to do? To get the mobilized angle of friction, you should do tan of phi m, you should make tan of phi m is equal to tan of phi m, that should be made equal to 2/3 of tan of phi. Are you getting? So basically if you do this, then only you will be able to get the mobilized angle of internal friction. So what will be the value of phi m? What will be the value of phi m? So phi m will be equal to tan inverse. So phi m will be ideally equal to, so you see ideally this phi m thus will be equal to tan, it will be equal to tan inverse, I am just writing this way, tan inverse 2/3 tan phi. Is it clear now? So once you get this mobilized angle of internal friction, see what is happening. For local shear failure, actually Cm you are changing to 2/3 C, and for local shear failure the value of phi, that is the angle of internal friction of the soil, you are changing it to phi m by this method, the tan inverse 2/3 tan phi. So through this, when you are getting the value of phi m, you will obviously notice from this that the value of your phi m, is going to be less than, the value of your phi. Okay, so let's say you started with a phi value, let's say of, let's say 36 degree, and maybe your calculated value of phi m after this doing tan inverse and all, I am not going to the exact calculation, it may become something like 29 degree or 32 degree, something like that. Okay, so if you get this value, that means when you are considering this local shear failure, then what actually is happening, you are ideally reducing the angle of internal friction. And you must understand at this point that with the reduction in angle of internal friction, these bearing capacity factor values, that is NC, NQ, N gamma values will change. So you see, basically you see this NC is NC, and then NQ, this NQ, and your N gamma, all these three things which are nothing but your bearing capacity factors, these are basically dependent on, they are function of this phi, right? They are function of I write it here, angle of internal friction, right? So when they are the function of angle of internal friction, if the value changes from phi to phi m, then and phi m is lesser than this phi, then what will happen? So if you put here 36 degree, so if you want to find out the NC, NQ, N gamma value for 36 degree, and when you changed this value from this 36 degree to this mobilized value, which will be lesser than your this value of phi, so instead 36 degree, let's say mobilized value becomes something like 31 degree. So 36 degree, for 36 degree whatever value of NC, NQ, N gamma you have got, for 31 degree you are going to get some different value. So that's why for local shear failure Terzaghi has done one thing, he has put this changed values as NC dash, NQ dash and N gamma dash, and thus your this equation, which is true for general shear failure, strip footing and net ultimate bearing capacity, this will change to this form with this 2/3 factor will come in front of C. NC will become NC dash, gamma these are going to remain same, NQ will become NQ dash, and this gamma B will remain same, and N gamma will become N gamma dash. Is this clear? So this formula is now given as IS 6403. This is general shear failure instead of general shear failure. This is the formula for local shear failure. You should understand it very clearly. So this is actually for local shear failure, and you understand now why this 2/3 is coming and why these NC dash, NQ dash, N gamma dash are coming. So NC dash, NQ dash, N gamma dash, they are nothing but the changed values of bearing capacity factor considering the values of mobilized angle of internal friction. And if you go back to the code, you see you are going to get exactly the same value. So sorry, here we should also give, here you should also write QD dash, because this is local shear failure criteria. And if you go to the code, you see code is also saying exactly the same value, same factor. You see, I'll just copy and paste it over here and to match it. So you see, this is what is code is saying. QD dash is equal to, this is little bit blurry, so 2/3, this is nothing but 2/3 C NC dash, you see, C NC dash, and Q is nothing but gamma D, then NQ dash we have written -1 plus half 0.5 gamma, this is gamma, then B and N gamma dash, and this is what is actually the net ultimate bearing capacity formula for local shear failure condition and for strip footing, and that is what is being defined in Indian Standard Code. I hope you should understand now. Is it clear now? Any doubt?
Sir,
Bolo.
sir, 2/3 equal to 0.5, sir.
Yes, tell me. और एक बार बोलो.
Sir, 2/3 equal to 0.5.
2/3.
Yes, sir.
Where 2/3 I have written 0.5.
No, sir. In code given 2/3 B gamma N dash gamma.
Pardon?
Sir, in code given, in case of local shear failure Q dash D.
I am not getting you. Little bit
Sir,
louder.
in code.
Yes. Bolo.
Sir, in code,
Hmm.
the net ultimate bearing capacity in local shear failure
Yes.
is equal to 2/3 C and S C.
2/3. This one, na? This one is actually 2/3.
No, sir. Third term.
Third term. Okay, just a minute.
2/3 B gamma N.
This one you are saying. Huh?
Yes, sir.
Bolo. Yes.
Sir,
This
sir,
one is
2/3.
1/2. This is 1/2.
Okay, sir.
Is it okay?
I think this is 2/3, sir.
No, this is not
Yes,
2
sir,
by
okay.
3. This is not 2 by 3. This is 1 by 2. See, this is the. See, you can
Okay.
take another one download of the code maybe. Okay, this is 1 by 2. This is not 2 by 3. This part. Okay. Okay.
Okay, sir.
Okay.
Yes.
So see, now how do you get these values of NC, NQ, N gamma? These values can be obtained from table 1, and that is given in Indian Standard Code. In this code only, if you go little down, then you will be getting a table 1 just below this. Okay. So you see, in this table 1 is given bearing capacity factors, and bearing capacity factors are given for phi, right? So if this phi is being changed to phi m, then once you change this to phi m, so considering the value of phi m, you calculate the values of nc, nq, n gamma, and that actually will be becoming your nc dash, nq dash, and n gamma dash. So see, this is what we have explained. Calculate phi dash equal to tan inverse 0.67 tan phi. Then read nc, nq, n gamma from the table corresponding to what? Corresponding to the value of phi dash. Phi dash means in this case in the Word document what I have written it phi m, mobilized shear strength, instead of phi, which are values of nc dash, nq dash, and n gamma dash. So see, for nc dash, nq dash, n gamma dash, you need not to have another one table. They are the same values which you will be using for the phi. Only thing what you will have to do for local shear failure criteria, you will have to change the value of phi before starting the problem. That means you will have to change it to mobilized shear strength parameter value. Okay. Okay. Let's move to the next part. So you see, next is, let us go to our PPT, and so you see this next clause, that is 5.1.2, if you see, that is page number 8, for net ultimate bearing capacity. So see, in the previous formula whatever we have seen it for strip footing. That's what we have written also, right? So strip footing, general shear failure, local shear failure, we have understood. Now if we want to have this formula for any kind of footing, okay, for any type of footing, so considering any type of footing or any shape of the footing, then any shape of the footing, or considering the inclination of the loading, depth of the embedment, and effect of water table. So all these things we have discussed for Terzaghis formula. Only thing we haven't discussed, that is the inclination of loading and depth of embedment. Okay, so these two things we have not discussed, but if you remember, we have discussed what is the effect of shape of footing and what is the effect of water table on the footing. Okay, so considering this, if we want to have Terzaghis, I want to have the bearing capacity formula, then Indian Standard Code has introduced another two factors like the shape factors, and they are called depth factor and inclination factor. They are just written as dc, dq, d gamma, and ic, iq, I gamma. So previously when we have discussed about Terzaghis bearing capacity, and we have said that it is valid for strip footing, but Terzaghi only has said that if you want to apply it for rectangular footing, circular footing, square footing, in such case you just change the formula by multiplying the bearing capacity factors, that is NC, NQ, N gamma, with the shape factor values, and those shape factors are defined by Terzaghi. Exactly the same way what Indian Standard Code has done, it has followed post Terzaghi some equation. So post Terzaghi, different scientists, different soil mechanics have given different formula. So considering that, Indian Standard Code has assumed the formula which has been given by Meyerhof. Okay, so considering Meyerhof's formula, Indian Standard Code has adopted another two factors which is being introduced in the formula as given by Terzaghi, and that is, and those factors are nothing but the inclination factor, which will take care about any load which is acting on the footing or on the column at an inclined position, and the second one is the embedment or depth of embedment factor, or in simple term it is called depth factor. And this depth factor is nothing but your depth of embedment, that is how much depth below the how much depth at what depth the footing is being placed. Depending on that and depending on the width of the footing, this is being defined what will be the depth factor of the footing. Now considering this, I am again going back to this one, and I'll try to show you what is being done and what is being changed. See, it is very simple to remember, you see. So we have said for strip footing, so 6403, if you remember, if you see, just today we have discussed for IS 6403. So IS 6403 has said for general shear failure, strip footing, net ultimate bearing capacity is this: CNC gamma D NQ minus 1, 0.5 gamma B N gamma. Now if I want to change this for general shear failure and for any kind of footing, so I am trying to do it for any kind of footing. So for any kind of footing, considering the effect of inclination of load, and considering the effect of depth of embedment. So if I want to consider these three things into account, what I'll have to do, you will have to just change this formula and introduce different factors for each of these. So any kind of footing means shape of the footing. Let us write shape of the footing. So shape of the footing. So shape of the footing, for shape of the footing you need to introduce three factors. So three factors means for each of the bearing capacity factors. So to NC there will be a factor, to NQ there will be a factor, to N gamma there will be a factor. Okay. So for each of these factors you need to introduce a factor, and you see that is what is being done here also. So what you will have to do, you need to introduce a factor NC. After this NC you will have to introduce a factor SC. This is nothing but your shape factor for this bearing capacity factor NC. So what you are introducing? You are introducing SC. So you are introducing SC. Then for this NQ factor you need to introduce another one factor, which will be SQ, and this is the shape factor introduced to take care about the shape of the footing. And then you will have to introduce another one shape factor for considering this N gamma, and that is going to be your S gamma. Okay, so this is going to be your S gamma, and this is going to become something like this. So you see, so S gamma factor if you are introducing, so see this form of equation exactly you have seen from Terzaghi. Okay, so this SC SQ S gamma, what the code is now saying, that we will understand later. What is the value of the code? Just let me little bit increase this font, otherwise it will be a little bit clear. So you see, so CNC SC, then gamma D NQ minus 1 SQ, SC, then gamma D NQ minus 1, then SQ, then 0.5 gamma B N gamma S gamma. Okay, now you see these three factors are shape factors. So what we have included? We have included the shape of the footing into consideration in this formula. Now if I want to include the effect of inclination of load exactly the same way Terzaghi has introduced these three factors for shape. We will have to introduce another three factors, and we will be writing here IC. So inclination factor we will be writing like IC, then here we will write I, here we will write IQ, and here we will write into I gamma. Okay, so these three factors are going to take care for the inclination of the load. So what will be the values of these IC, IQ and I gamma that is being defined by Indian Standard Code, which has adopted the formulation from basically the Meyerhoff's formulation. Okay, so it's not Terzaghi, it's Meyerhoff's formulation. So from the Meyerhoff's formulation, it has adopted something and it has defined the value of IC, IQ, I gamma. We'll come to that in a later part, and we'll show you what is the value, what are the values for IC, IQ and I gamma. So once you have taken the effect of inclination of load, the next part you see only the left part is now effect of depth of embedment. So if you want to take the effect of depth of embedment, in that case what you will have to do? You will have to introduce another three factors, and that is being considered in the code as DC. So you introduce another one factor DC to this NC factor, and then there will be obviously another one factor DQ, and there will be another one factor, see there will be another one factor over here, that will be D gamma. Okay, so D gamma. So if you see this equation ideally, if you notice, this is actually Terzaghi's equation only. Only it has been taken in a different form. Okay, and Terzaghi has introduced only these factors SC, SQ. Terzaghi has only introduced these three factors, right? SC, SQ and S gamma. Instead, Indian Standard Code has introduced another two factors, which are nothing but this IC, IQ. So Indian Standard Code new factors are IC, which is being followed from some other codes, which is being followed by some other methodologies. Okay, and these factors, this IC, IQ and I gamma, these are being considered to take care about the effect of inclination of load. And on the third part, you see that to take care of the effect of depth of embedment, if you see, these three factors are taken. This is DC, then DQ and D gamma. So you see, if you observe now this equation, now in this form, in this Indian Standard Code, you see you are going to get exactly the same form. So in case of general shear failure, I am just bringing this equation in front of you in this Word document. You see, they are, this is you notice this is the same equation. We'll come to this WD dash factor later. Okay, first you forget about this WD dash and you see whether we have written this equation in the correct form of Indian Standard Code or not. So you see what is being done, exactly the same equation of Terzaghi is remaining, only you are introducing two factors, inclination extra factors, that is inclination factor to take care about the effect of inclined load, and the depth factor, so which will be taking care about the effect of depth of embedment. So what are the three factors we have introduced? One is your shape factor, the second one is your inclination factor, and the third one is your depth factor. Now for each of these factors, shape factor, inclination factor and depth factor, you need to know what will be the values for SC, SQ, S gamma, then IC, IQ, I gamma, DC, DQ, D gamma, and code, Indian Standard Code defines all these values separately. Okay, so if you see Indian Standard Code, we will be seeing in later part of this discussion that these values are specified in Indian Standard Code. Now forget about this W dash. This is actually let's not forget, let's take into account this one. So this W dash, what is this W dash? See, this W dash is nothing but the water table correction factor. If you go to Indian Standard Code, you see Indian Standard Code defines it somewhere. So you see here it is said effect of water table. So this formula is taking care about the shape of the footing, inclination of loading, depth of amendment and effect of water table. So to take care about the effect of water table, you need to multiply it with W dash. Okay. Now the value of W dash, I have explained you how to calculate the value of W dash. Now here one confusion may arise in front of you, that in the previous equation when we have discussed about the water table correction factor, in that if you remember, we have multiplied RW1 or W1 factor to this and then W2 factor to this, right? Instead, you see in the Indian Standard Code only one factor is being considered. So you see only the breadth portion of the formula that is being impacted by the water table correction factor, whereas the depth portion of the formula, that is which is considering gamma D, that depth portion of formula is not being impacted by the water table correction factor. Instead, what you should be doing, applying the Indian Standard Code formula, if you see that your water table is rising above the base of the footing, in such case what you will have to do, in this Q value there is a gamma D, this Q is nothing but gamma D. So instead of applying the RW1 factor, you can use RW1 factor here also and modify the value of gamma, or Indian Standard Code says that other than that what you can do, you can take the exact value of gamma, okay. So exact value of gamma you can use in place of this gamma D, okay. So that is why Indian Standard Code has not taken this RW1 factor or W1 factor in this equation. However, if you go with that RW1 factor also, it will not impact your bearing capacity calculation much, because I have explained you that the effect of RW1 is nothing but to reduce the value of the bulk unit weight or the saturated unit weight of the soil when the water table is rising up the soil, rising up the base of the footing, and in that way the soil is either getting fully submerged or partially submerged. So when the soil is getting fully submerged or partially submerged, ideally the unit weight of the soil needs to be reduced, okay. So after this if you see, if you change this formula, so if you want to apply this formula for the local shear failure criteria, see this formula will take, it will remain in the same form, right? It will remain in the same form, only you see you will be changing this formula to 2/3 of C. That is what we have done, you see earlier also, that is what we have done, and this will become NC dash, and then this will become NQ dash, NQ dash, and this will become N gamma dash, Is it clear? So you see, that is what is the code is also saying. You see, the code is also saying that. So if you notice, the code is also saying same thing. So for local shear failure, if you see, the code is saying this is. So if you go for this, see exactly the same thing we have written for local shear failure. For local shear failure, you see, we have written 2/3 of C, NC dash, SC, IC, DC. See, it need not to be changed. See, SC, IC, DC, these quantities depend on the shape of the footing, inclination of the load, and depth of embedment. These factors are not dependent on the value of angle of internal resistance. So these factors will remain unimpacted because of the local shear failure criteria. You must understand this. Only the values will be changing for this NC dash, because of the local shear failure, your mobilized angle of friction will be lesser than whatever angle of friction the soil is having, and then your NQ dash, this will also depend on your phi m value, and then N gamma dash, this will also depend on your phi m value. So these three things are going to change. That means your bearing capacity factors are going to change. Your C value is going to become 2/3 of C. However, your shape factor, inclination factor, DC, depth factors all will remain same. The effect of water table will also remain same in case of the local shear failure criteria also. So this is the primary part of understanding about your Indian Standard Code 6403 and how to calculate bearing capacity for any kind of footing, taking into the effect of different shape of footing, inclination of load, depth of embedment, and water table. Okay, so we will be discussing in the next class about how to calculate these different factor values. So Indian Standard Code specifies the values to calculate these things, and formula wise you will have to remember them, or you will have to follow the code, and according to the codal provision you will have to calculate the value and apply in the formula to get the get the bearing capacity value. Okay, so I think today we stop here. If you have any question up to this, you can ask. Any question? Why only 14 members are coming?
No, sir, 31 members.
Huh? 31 is there, na?
Yes.
Why 14 are coming?
रिफ्रेश कीजिए सर.
Refresh किया. Just a minute. 31. Now it is 31. They are coming now, or again should I refresh? (32). Just a minute. Again I refresh and take the download. Okay. 32. I don't know. Okay. So I have taken the attendance from here. Let me take a print screen for this and let's finish. So do you have any question? Ask, tell me fast. বলো।
No, sir.
স্যার এখানে আমরা দুটো ইকুয়েশন পেলাম, এই দুটো মানে জেনারেল শেয়ার ফেলিয়ার আর লোকাল শেয়ার।
Ask in English. Try make a habit, okay, speaking in English, okay. Otherwise see interviews and all you'll have to speak in English. So please try it. Bolo, tell me. Subhadip, ask. Hello.
Sir, is this two equations are general equation for general shear failure and local shear failure?
Yes, these two equations, whatever we have got, okay, these
Huh,
two
yes, sir.
equations finally, okay. So this equation is for general shear failure. These are general equation. So you
Yes,
can
sir.
apply it for any footing, okay. You can apply it for strip footing, you can apply for rectangular footing, square footing, circular footing. You can apply it when the load is acting vertically on the footing, or whether the load is acting at an inclined level on the footing. You can apply this formula when the footing is at 1 meter depth, 2 meter depth, 3 meter depth. With a ratio between df and b, you can calculate the effect of depth of embankment, and you can apply it. You can apply this formula considering the effect of water table, okay. So this formula is the most generic formula you can have, okay. So this takes into account everything about bearing capacity, and that is what is Indian Standard Code 6403 formula, okay. It is little different than Terzaghi, but you see Terzaghi's concepts are not being it's not that Terzaghi's concepts are not taken. It is coming from Terzaghi. Terzaghi is the father of it, okay, bearing capacity equation. So from Terzaghi's formula, many researchers have modified it, changed it, have considered different other effects, and then gradually it modified. So Indian Standard Code has taken the consideration from Meyerhoff's formula, which is being taken from Terzaghi, and from that formula Indian Standard Code has introduced this formula, and the values of SC, IC, DC, these are being calculated and taken in Indian Standard Code as per the recommendation given by Indian standards, okay. Is it clear?
Yes, sir.
Okay. Any other question? So should I stop? If you have any question, you can ask, or then otherwise I'll stop.
Yes, sir.
Okay. Thank you. See you next week. Okay. Okay.